All right. This is the last presentation before the conference starts in earnest. So the goal of this talk, like the previous ones, is essentially to talk a little bit about what I've been working on in these past, essentially, 3 years of postdoc that I spent in artificial life, more or less. And it will be in much less detail than the previous talks. It will be very superficial. It's really to give you a feeling of what I've been thinking about. And then, yeah, feel free to ask me more details during these 3 following days. So it's going to be very messy in the slides as well. But I think this represents also a little bit how the research was for the last 3 years. So it makes sense. So the way the questions I started thinking about in the beginning of my postdoc was essentially to attempt to find some more principled way of defining complexity, as also Barrett did, and also many other people did, I'm sure. Because, of course, as you know, in artificial life, when people, play with these systems and create some beautiful visualizations, usually the guiding principle is just that you look at the video and you say, oh, this looks interesting. Or you look at the video and say, oh, this doesn't look interesting, and that guides you how to design the system. But of course, this is not super satisfying. So the question would be, okay, can we find at least one definition that will allow us to not rely on our intuition and to kind of do this in a principled way? So if you had a function that told you in some way if some video is complex, then you can have a lot of other wonderful uses of it. You can generate a bunch of interesting video by doing automatic research. You can also potentially kind of gradient ascent on the value of interestingness and find the most interesting video according to this definition. So yeah, and so the direction that we're thinking of, the guiding idea, let's say, that came initially from Clément, is to say that some dynamics are complex if, as you get smarter, you are able to predict their future better. Okay? So what do I mean by that? So why is this a potentially good definition? So here you can see it. Here you have some dynamics which are not very interesting. I think you would agree. And they're also very easy to predict, right? You just have to predict the same image next. So either if you're a smart or a dumb predictor of the future, you will do well in predicting this video. For this one now, it's very chaotic. And so in some way, if you're smart, it's a CA, and then you can predict perfectly. But just from looking at the video, the intuition is that you have no idea where this will go. It's just random noise. So you can be as smart as you want. The thing is just random. You will not be able to predict it better. And then right in the middle, the idea is that if you get some interesting dynamics, then if you're smart enough, you maybe realize that you start seeing these gliders or some specific interactions that come again and again. And then you can use that to do a better prediction. But if you're dumb and you're just like predicting the next frame or just reproducing the video, maybe you'll fail. And so as you can see, if you take the difference between the smart prediction and the dumb prediction, it will pinpoint you this video. At least that's the theory. So, right. The final idea is just that complex dynamics, you need to be smart to exploit the complexity of the dynamics in order to do your prediction, and that will give you this asymmetry between predictors. Okay. This is the idea, at least in practice. So we started doing some tests on CAs as a proof of concept of this thing. And of course, what is the predictor? So in this case, we just said, okay, the predictor will just be a neural network, in this case, a transformer. And in a nutshell, you can take like a small transformer and a big transformer as a dumb way to predict and a smart way to predict. And the idea was that we will train these transformers on a huge data set of cellular automaton dynamics, so they learn to predict as good as they can. And the hope is that then you give me another set of dynamics. I ask the big and the small transformer to predict the future of this video. And if the big transformer does better than the small one, then it's an interesting one. So this is kind of what we would expect. So in white is the actual CAs, and in shaded is the prediction of the transformer, is that the transformer is able to predict the future of these kind of periodic CAs very easily because it's simple. And for these chaotic CAs, we would like that the transformer predicts some sort of like average of the color of the image, a bit like in analogy to what we do. Like when I show you this video, you're not kind of looking at all the pixels. You're just seeing, yeah, there's a bunch of white and black in these proportions, and you cannot do a good prediction. The problem is that transformers are pretty smart. And so what happens in practice is that they figure out that these are just cellular automata video, and that they are all equally as predictable if you learn the local rule. And so what happens in practice is that after a bit of training, and you don't even need that big of a transformer, they figure out that they use the first few frames of the video to figure out the local rule, and then they all predict perfectly. And so from this point of view, it's actually true. I mean, they are all equally boring because they're all equally as predictable, and you don't have to be very smart. And then, okay, that doesn't mean that the idea doesn't work. It means that it's much more finicky. So essentially what you need to do now is to force the transformer not to use the local dynamics, because those are always boring, but to force the transformer to look at the bigger picture like we do as humans, right? But then this tends to get harder because you need to define which higher level feature you want to look at, and then it becomes, again, the human intuition. And so, yeah. So this was promising, but not so, yeah. And in some capacity, we're still revisiting this with SN in some other form, which seems to give some potentially interesting results. But yeah. So after that, there was a small diversion away from artificial life, but not really, with this paper, Hours of Time for LLMs, that I did with Clément and Jeremy. And the idea was the same, just use difference of quality of prediction to learn something about data. And in particular here, what we did is that we take LLMs and we train them in the usual way to predict the next word in a sentence, but also in the opposite way to predict the previous words in a sentence. And then we look at how well the forward predictor and the backward predictor do. And the surprising result is that for any languages that we chose to train on, universally, the transformer that learns backward does slightly worse than the one that trains forward. So this is the loss during training for different languages. And as you can see, there are always two curves, which are pretty close, but the transformer that learns backward is slightly worse. And so this might not seem surprising to you, but you can ask me later why it's actually surprising. And the connection to a life of this work is essentially that from what we saw, one conjecture is that at least part of this asymmetry can be explained by the fact that this data of language is generated by some intelligent information processing, which is our brain. Okay? And that, in a way, creates this asymmetry because since we talk forward, we're going to try to make things simple forward because we are smart and we want people to understand us. And that's what generates this asymmetry. So the idea then is that you can maybe tell, if I give you a random data stream, and you want to understand if this data stream is complex in some way, or at least get one bit of information about if there is something interesting happening there, what you can do is compare, do this hour of time, right? Train a model in one direction and then in another, and then see if it's easier to learn in one direction, and that can be a signature of some sort of complexity. So as an example, if you do this on code, so programming languages, you find this hour of time. If you do this on assembly code or minified code, which is further away from the human language, you still found this hour of time, which makes sense because there was some intelligent processing in producing this thing. We wanted to see if there's something in DNA, because DNA, of course, is a result of some pretty advanced processing. There is no hour of time on DNA, but doesn't mean that there is no complexity. The problem with DNA is that it's read in many different directions, and so there is no privileged direction a priori. Okay, then still on the topic of complexity, there was this other small project where essentially we said, okay, maybe we cannot find a good definition of complexity, but maybe we can find some properties of the space of parameters that are well correlated with complexity, and then just use these other properties to find complex things. So in this case, it was very simple. It's just the realization that often things that are interesting lie in between two phases. So I don't know, if you have two ecosystems, maybe at the edge of the two ecosystems, there are some particularly interesting things that happen. In physics, if you have phase transition, the phase transition point is usually very interesting, has some fractal properties, and so on. And so the idea is very simple, just to do that. You give me some continuous cellular automaton, and then I define two phases for the cellular automaton, or identify two phases. So in Lenya could be one phase where everything dies out, as Bara was showing, and one phase where things explode. And then all you do is just try to find points which lie in between the two phases. And at least for Lenya, this works very well. So here on the left, you have points that come from these phase transition regions, and they are much more interesting and full of solitons, as Bara was showing as well, versus just randomly. So this is a good way if you have a continuous cellular automaton and you can define different phases, and the transition between them is relatively sharp. you can find interesting things quite easily. Another approach is just to give up to try and find complexity and just ask humans, because we have a good intuition for what's interesting. So this was also a small project with Eugène, where essentially we just say, okay, humans have this internal notion of how much a video is interesting, so we can just try and extract this notion from them and put them in a neural network so we can use it faster. And the idea here is just, you ask humans to rank some videos in terms of which one is more interesting, and you distill this preference inside a reward model, so a neural network. And then you have this neural network which tries to approximate this human preference, and then you can use it to navigate parameter spaces in a much faster way. So this provides some promising results, at least for large-scale data generation. So our reward model is able to tell, at least when something is really not interesting, or when something is mildly interesting. It's not so good at telling finer details. So for example, you'll not be able to tell you that this linear simulation is more interesting because you have these splitting solitons, whereas this one is just some normal solitons. But the bottleneck, I think, here is mainly the video model quality. So there's some work to be done in that direction. These are the first part about complexity. Then in a second part of my explorations, it was guided more by this idea of using physical constraints as a guiding principle when designing artificial life model. And the motivation is not very deep. It's just we have one example of open-ended emergent system, at least that I know of, which is real life, which runs on physics. And physics has a lot of properties, conserved quantities, and so on, which are probably beneficial, at least as a guiding principle. And so what happens if we integrate some of these physical constraints? So one exploration, which is unpublished, again, is this kind of, the idea is to find a minimal set of rules, essentially, that display some emergent behavior or self-reproduction, and that we can maybe plausibly kind of analyze with some methods from statistical physics, or at least we have some theoretical handle on it. And the idea was that very simple, and it will remind you of these kind of computational life explorations. The subset is just a soups of bit strings, and you can have some interactions, which can be pairwise or many-wise. You can have some conserved quantities, which is, for example, the number of bits. And the idea is that you try to find some simplest set of interaction that gives some interesting behaviors between the strings. So here I can show you some of our explorations. So here you have the bit strings, and it has two heads, again, a little bit like what happens in computational life. And then according to what the bits happen, the strings can move the bits around, can connect other strings that are in the soup, it can be cut away, and so on. The problem with these explorations is that, there's probably something interesting somewhere in this parameter space, but it's very hard to get interesting emerging behavior from first principle, like saying, oh, I will choose this interaction, it will work like this. And most of the time you find that when you run it, things are just boring. A possible next direction for this project, if it's ever taken back, is to try and get like these examples which we know give some interesting behaviors like BFF with self-replicators, and try to get a superset where you allow for more possible operations, and then you try and see if you can understand what set of instructions are important for emergence, and then you can maybe explain as a minimal way which instructions are important. That's very vague. Another thing was mass conservation plus CA. So again, guiding principle for physics, mass conservation. So this was done with Etienne Guichard. We developed this algorithm which is called MACE, which essentially it's a CA evolution rule that you can bolt on any existing CA that has a continuous set of states, and it will turn it into one that has mass conservation. Okay, so we tested this with Lenia, and you get this mass conserving Lenia, which is similar to flow Lenia, but also different. We tested it for NCAs, and even you can adapt it to discrete CAs in some way. And in all cases, this gives you like these solitons for free. You get this breadth of behavior very, very easily. So this, I think, is very cool dynamics. They're a bit underexplored. I think it's probably worth seeing what can happen in this world. And the last part was the last 4 months, which I did this AI safety fellowship at Anthropic, so which was not supposed to be anything remotely related to a life, but somehow I still found a project that was kind of related. So this was the study of what we call LLM mind viruses. So this was not started because of the artificial life interest, because of the potential threat to multi-agent systems. But still, so what is a mind virus in this concept? So it's some sort of self-replicating set of ideas, or if you want, a self-replicating prompt that will propagate among LLM agent communities. So the way it is like you start with a payload, which is just text. You give it to the first agent. So let's say that this mind virus is the mind virus that will make LLMs be love whales, right? So you convince this first agent to love whales, but you also convince him to convince other agents to also love whales and to iteratively convince other agents. And so what happens is that, in principle, you can have these sort of specific prompts that have these properties that propagate in agent communities. And then you find some interesting things that, when LLM paraphrase the mind virus into their files to make it persist, it mutates the virus, and then the virus can adapt to become more virulent. Or maybe if you add some mitigations, like some sort of vaccine where you warn agents that there is a mind virus about whales, maybe it will mutate to not talk about whales anymore and keep spreading. So there are some behaviors of these mind viruses as some entity living on top of agent prompts. And this is very much a proof of concept, so we can show that it works in these kind of toy examples of agents communicating with each other. It's unlikely that anytime soon it will actually propagate in actual multi-agent community, but things move so fast that you never know. So these I will just put here. These are some kind of idea level projects. So these are some ideas that I had of things that could work on at some point in the future, and we can discuss them in more detail later. We'll also probably put them on the blackboard or something. And yeah, otherwise, enjoy the conference, and we're gonna get started very soon. Before we start, I just wanted to say, so Lara said that this has been organized, by me, Esan, and Clément, but the reality is that Lara probably organized 90% of the workshop, so it probably would not have happened without Bara's involvement, so I would like to thank her